Welcome to the online narrated lectures for CM2101. In week 8 we will finish our discussion of vibrational spectroscopy. This week we will be looking at polyatomic systems, and we will begin by discussing the normal modes of polyatomic molecules. When we were studying diatomic molecules last week, we realized of course that there is only one vibration. There is only one bond. There cannot possibly be more than one vibration. With polyatomic molecules, we can certainly have more than one mode of vibration, and we refer to these modes of vibration as normal modes. But I will define exactly what we mean by normal modes later. Because diatomic molecules have only one mode of vibration, there was only a single fundamental band. With polyatomic molecules, we can imagine that we can have a fundamental band associated with each normal mode of vibration, assuming that all the normal modes are non-degenerate and infrared active. Let's have a look at two triatomic molecules and see how many fundamental bands are visible in the infrared. First, let's have a look at water. In this spectrum you can see three peaks. One is relatively low frequency of 1595 wave numbers, and two at higher frequencies at 3652 and 3756 wave numbers. Next then, let's look at carbon dioxide. In this spectrum you can see two peaks due to carbon dioxide at 667 wave numbers and 2349 wave numbers. The peaks around 3700 wave numbers are due to water. So despite these two molecules having the same number of atoms and the same number of bonds, they exhibit different number of peaks. We will see that what determines the number of peaks is not just the number of possible vibrations in the molecule, but also whether the vibrations are degenerate and whether the vibrations are intrinsically infrared active. Let's first discuss what determines how many vibrations a molecule can have. Both water and carbon dioxide have three atoms, but do they have the same number of vibrations? How many different ways can they vibrate? Let's look at a triatomic molecule. We describe the position of each atom in the molecule with three coordinates. This means that in order to describe the motion of each atom, we also require three coordinates for each atom. We can say that each atom has 3 degrees of freedom. If we had but a single atom in the system, then each of these 3 degrees of freedom would be purely translational in nature. If we had a diatomic molecule, then we would need 6 coordinates to describe the motion of both atoms, and thus there would be 6 degrees of freedom. The motion of 3 atoms in a triatomic molecule would require 9 coordinates, and there would be 9 degrees of freedom. In a polyatomic molecule of n atoms, therefore, there are 3 times n degrees of freedom. When we have more than one atom, these degrees of freedom can be written as combinations of the atomic coordinates that describe translations, vibrations, and rotations. First, let's look at translational motion. To describe the position of a molecule, we can specify its center of mass with 3 coordinates. We can then describe the translation of a molecule from one position to another by identifying the change in the 3 coordinates of its center of mass. Therefore, every molecule has 3 translational degrees of freedom. A pure translation is one in which, during the motion, there is no relative change in the internal coordinates of the molecule, i.e. no rotation and no vibration. So of the 3 n degrees of freedom for our polyatomic molecule of n atoms, 3 of those degrees of freedom can be identified as pure translations. To describe a rotation of a linear molecule, we require 2 angular coordinates. These angles can be the azimuth, which is depicted here as phi, and colatitude, which is depicted here as theta, in the spherical coordinates that I've shown in this figure. In the same way as when we discuss linear molecules, we discuss rotation in terms of two component rotational axes. Therefore, for linear molecules we have two rotational degrees of freedom. This enables us to determine the number of vibrations in a linear system. The number of vibrations is simply the number of degrees of freedom, which is 3 times n, minus the number of translational and rotational degrees of freedom. This will be 3n minus 3 for the translations and minus 2 for the rotations. So overall, therefore, a linear molecule has 3n minus 5 vibrations. In a nonlinear molecule, we require 3 angular coordinates to describe motion. We have the azimuth and colatitudes as before, but we also need another angle to describe the molecule's internal rotation. Therefore, for a nonlinear molecule, we have 3 rotational degrees of freedom. This means that for a nonlinear system, the number of vibrations is once again simply the number of degrees of freedom, which is 3n, minus the number of translational and rotational degrees of freedom. This will be 3n minus 3 for the translations and minus 3 for the rotations. So overall, therefore, a nonlinear molecule has 3n minus 6 vibrations. This means that nonlinear systems have 1 fewer vibrations than linear systems with the same number of atoms. So let's return to our two triatomics, water and carbon dioxide. Water is a nonlinear molecule, and so we expect it to have 3n minus 6 vibrations. And as n is equal to 3, this means that water has 3 vibrational degrees of freedom. The infrared spectrum had 3 bands, so it would appear that all the bands are infrared active and non-degenerate. For carbon dioxide, we have a linear molecule, and so we expect 3n minus 5 vibrations. This means that carbon dioxide has 4 vibrational degrees of freedom. However, the infrared spectrum for carbon dioxide shows only 2 bands. I will explain this shortly. Before we continue, we need to formally define what we mean by normal modes of vibration. Any arbitrary set of displacements of atoms can be expressed as a superposition of 3n minus 6 in the case of a nonlinear molecule and 3n minus 5 in the case of a linear molecule, normal modes of vibration. A normal mode of vibration is one in which all the atoms move in phase with the same frequency. The center of mass remains fixed, so that there is no co-translational motion. The vibrational energy is quantized. The motion described is approximately simple harmonic. Each normal mode is independent and to a good approximation is not affected by the other normal modes. And finally, if the molecule starts vibrating in a normal mode, it will continue to do so. It will not transform into another normal mode. Let's see if we can understand this in terms of carbon dioxide. Vibrations frequently involve stretching of bonds. So let's consider the CO bonds in carbon dioxide vibrating separately. We would thus have a left bond vibration and a right bond vibration. However, these vibrations are not independent. If we excite the left vibration, then because this involves motion of the central carbon atom, the right bond will be affected and the right vibration will get excited. The normal modes of vibration associated with stretching in carbon dioxide are in fact a linear combination of the left and right vibrations. If we add the left and right vibrations together in phase, then we will get the symmetric stretch nu1. and if we add the left and right vibrations together out of phase, then we get the asymmetric stretch nu2. This time, exciting the symmetric stretch does not lead to the excitation of the asymmetric stretch. On the right, we have the 4 normal modes of vibration. You will notice the symmetric and the asymmetric stretches that we saw in the previous slide, but there are also 2 bending modes which have exactly the same frequency of 667 wave numbers. These bending modes are thus degenerate. You can see that the bending modes are related by symmetry. You can transform one mode into the other by rotating about the internuclear axis, which is of course a symmetry element for this molecule. The fact that the bending modes are degenerate explains why one band is missing from the infrared spectrum. If you excite the fundamental transitions of either bending mode, it occurs at exactly the same energy, and so the spectral lines will lie on top of each other. In this animation, you can see the symmetric stretch, the asymmetric stretch, the bending motion, and the superposition of all the modes. Let me show that again. Here we have the symmetric stretch, the asymmetric stretch, the bending mode, and a superposition of all 3. Notice that the bending mode have been added together in such a way that they look like a kind of rotation around the internuclear axis. I will try to illustrate this more clearly in class on Thursday. The superposition is simply the addition of all modes. The motion appears to be rather chaotic, but this is what you would see at the molecular level. It is important that although we discuss the vibrational modes separately, that you appreciate that the motion of the atoms is described as a linear combination of all the vibrational modes. Each normal mode has its own vibrational energy levels, each with their own set of vibrational quantum numbers. There are 4 vibrational quantum numbers, and if all these quantum states are 0, we can identify the 0-point energies associated with each of the modes. Note that the total 0-point energy of the molecule will simply be the sum of all the individual 0-point energies. It is the total 0-point energy that the molecule will have at 0 Kelvin. The gross selection rule remains the same as we saw in the diatomic system. The dipole moment must change as the vibration passes through the equilibrium position. Mathematically, this can be expressed as the gradient of the dipole moment with respect to the vibrational coordinate q evaluated at the equilibrium position, and for the molecule to be infrared active, this gradient must be non-zero. This selection rule is identical to that of the diatomic, except that the displacement is now a combination of atomic coordinates, that is, the normal coordinate q. Thus nu1 of carbon dioxide, the symmetric stretch, is infrared inactive as it does not generate a dipole moment at any point during the vibration. This explains why there are only 2 vibrational bands in the infrared spectrum of carbon dioxide rather than 4. One is missing because the 2 bending modes are degenerate, and a second is missing because the symmetric stretch is infrared inactive. This is the end of part 1 of this week's online lecture. Please continue on to part 2.